My dear friends. Today I am going to discuss with you a very important and very interesting phenomena. You know what is that? That is time dilation. So let's accompany with me for that topic. Thank you. Now, what is the time dilation? First of all, I'll explain to you what we mean by the proper time. And there is a quantity tau naught which is determined by the events that occur at the same place in an observer frame of reference. Okay, and that is called the proper time interval between the events. For example, if I am here on the earth and I do an experiment, very simple. I'm having something and I release, like I'm having this, ring, and I allow it to fall. Okay, then just the instant when I released, that will be the starting time, and when it hits to my hand, that is the last time. Then I noted down the time interval between the two. That is called the proper time because I am at rest. Now, second, I am in a spacecraft which is moving with some velocity, and I am in the spacecraft, and I then do the same experiment. I'm having this bracelet, and I just release from here, and I noted down the starting time when it hits, and again I noted down that time. I take the time difference, that's the time interval of this event, and that will be again the proper time because I am in the moving frame and I am observing this event myself at the same place. Even my spacecraft is moving, no problem, because I am the observer and I am in the spacecraft. That time will be again the proper time. So it is clear what we mean by, first of all, the proper time. Now I'm next coming what we mean by the time dilation. Okay. Okay, let's again. I'm in a spacecraft and spacecraft is moving with some velocity. And that was my experiment. Like I released it from here. Okay, and it hits my hand. I noted down the time in the spacecraft. I noted down myself, and that was the proper time. That is, T naught. Now what happened? Like when I was doing this experiment, then at the same time there was the observer on the ground. And that observer was also the witnessed. Okay, when witnessed from the ground, the same event that marked the beginning and end of this time interval. Now for the observer on the ground, if there is an observer on the ground, he noted down the same event. Then how he noted, when it was released, then because I am in a spacecraft, when it was released, then this I am and the blessed red, it was at this place. Okay. Now then when it was released, it took the time, to reach here, and within this time, because the spacecraft is moving, within this time, you know, myself and the spacecraft, it shifted from this place to this place. So it was released from here, but it was received, it was received, you know, at here. You know, by the observer, this is an observation by the observer which is on the ground, not by the observer which is in the spacecraft. I'm again repeating it. The event, okay, I was in the spacecraft, I did the event, I released it, and I received here, and by me the time was the proper, no problem. But the observer which is on the ground, when he noticed the same event, according to that observer which is on the ground, the event started at this place. Okay, but because the spacecraft is moving, starting was here, but the end of this event was not at here, because spacecraft is moving. So that's why the end of the event was not here, but it would be at this place. Who noticed it? Like this is happening like this to the observer which is on the ground. He noticed like this. The event is, event is starting at this place, but its end is at the different place. So this is the observation by the observer on the ground. So that's why whatever the time which he noticed will be different and will be delayed. Okay, will be delayed, will be more time. Delay means more time. That is called non-proper time, and we have to calculate that time. What is that? What is the time relation? Okay, the actual time means proper time and improper time. So please we go forward now. To see how the time dilation comes about, let us consider the two clocks. One clock is at rest in the laboratory on the ground, and other is in the spacecraft that moves at the speed v relative to the ground. In each clock, a pulse of light, in each clock, a pulse of light is reflected back and forth between the two mirrors at a distance L0 apart. Whenever the light strikes the lower mirror, an electrical pulse is produced. Like that, this is a set of the two mirrors. A light pulse is generated, at a point. A light pulse is generated here, and it started and it goes to the upper mirror, and then it is reflected back and comes down. Okay, and again strikes the lower mirror. When the light, it goes reflected back and moves down and again strikes the lower mirror, then that time interval will be noted down, and that is recorded by some device. What is time taken by the flash for moving up and down journey? Okay. So this is a laboratory clock, moving up and down, and this will be the proper time. Velocity is equals to distance over time. Distance moved L0 to this side and L0 back. So velocity is equals to distance over time. That time, this time will be recorded by some device. Now this time is the proper time. This time is the proper time. Okay. Now a light pulse clock is now in a spacecraft as seen by observer on the ground. Now we are looking at a situation. Okay. We are looking at a situation that we are in a spacecraft. Again, there are two mirrors, this one and this one. And when we are in the spacecraft, again a light pulse will be generated and it moves up and strikes the upper mirror, then reflected down and will be recorded. If it is recorded by us, by me, when I am in the spacecraft, that will be again the proper time. But you think a situation when this event will be noticed by an observer on the ground. So what happens for an observer on the ground? So what happens for an observer on the ground? You know what happens, like now I am talking the situation which is for an observer which is on the ground and the event is in the spacecraft. Okay, the event is of the spacecraft. It is in the spacecraft. A light pulse is generated. It is generated. When it is generated, that time is zero. That time is zero. Now what happens when it is generated? Because spacecraft is moving along this side. So after some time, let assume that after half time of let t is the total time of the event. And after half time, the spacecraft position will be shifted as noticed by an observer which is on the ground. He noticed that now the mirror which was here after time t by 2 will not be at this place but will be at this place. And now because the light is again reflected back, that means the upper mirror is also shifted from this place to this place. That means the light which was generated at here will be reflected back not at this place but will be reflected back when the mirror was at this place. Okay, now this is very important. But the time, time of reaching the spacecraft from here to here is t by 2. Now the time taken by the light with velocity c for reaching from this point to this point should be again of t by 2. That's why the light will be reflected back again. So now think over it. Now what is this distance? This distance will be, what is the distance? Velocity is equal to distance over time, and distance is equal to velocity into time. So distance is v into t by 2, and this distance will be c into t by 2, and this distance is the distance between the two mirrors, which is L naught. Now using the Pythagoras theorem, now this is all noticed by the observer which is on the ground. This is very important. Now using the Pythagoras theorem, hypotenuse square is equals to base square plus perpendicular square. Okay, and just solving the mathematics, which is very simple here. Now we'll calculate the t, which is non-proper time, and this is the time which is observed by the observer on the ground. So okay, so this is equals to, now c square taken as common from the denominator, and t square becomes equals to this. You know, this t will be equals to this expression. Now again, when the event was noticed by the observer, which is in the spacecraft, that will be the proper time, 12 naught by c. 12 naught by c is the proper time. And you know, this proper time is t naught. So non-proper time becomes t, which is observed by the observer on the ground. So this is the final relation. Okay, this is the final relation. T is that time which is observed by the observer on the ground. T naught is the proper time which is observed by the observer which is in the spacecraft. Okay, and for the observer on the ground, the spacecraft is moving with velocity v. You know, like a very important point, this relation is applicable when velocity of the object is very large, velocity of the spacecraft is very large, reaches to the velocity of light. For smaller velocity, v square over c square may be neglected, approximately 0. Then t and t naught will be the same. So for low velocities, the relation is this relation is not having any significance. Now what about the analysis of this relation? Okay, now this factor 1 over root of v square over c square is always smaller than 1. Mean the denominator always exists in fraction. The denominator will be in fraction less than 1. So that means t will be greater than t naught. T naught was the proper time and t is the improper time as noticed by the observer on the ground, and he noticed an interval, an event which was happened in the moving frame. Okay, when he noticed the event which was in the moving frame, the observer on the ground noticed that the time is t, and that time is mathematically, it comes out the greater than t naught. Okay, because denominator is smaller than 1 always. So the moving clock is in a spacecraft appear to, so moving clock appears to be slow at, okay, moving clock in the spacecraft appear to click at a slower rate. Now exactly the same analysis holds for the measurement of the clock on the ground by the pilot of the spacecraft. Here I mean to say, if there is a pilot in the spacecraft and he noticed something which is happening on the ground, okay, then for the pilot, again the time interval of the event will be greater than the time interval of the event which will be noted by the observer on the ground, because the pilot is observing the event which is happening on the ground. So for the pilot, the time will be delayed. For the pilot, the time will be delayed. To him, the light pulse of the ground clock follows a zigzag path, and that requires a total time t per round trip, which is greater than t naught, the exact time. So total time t per round trip, he is on clock at rest in the spacecraft. He too finds the same relation. I mean, the relation is reciprocal. If that you are in the spacecraft and you are observing something on the earth which is happening here, and then for you the time will be delayed. Okay, for you the time will be delayed. And if you are on the earth and something is happening in the spacecraft and you are observing the event, then for you, because you are on the earth, the time will be delayed. So this is the time which is noticed by the observer, which is not at that place where the event is happening. This is very important. This is the time for the observer which is not at that place where the event is happening. This is the time for the observer which is there where the event is happening. So the effect is reciprocal. So every observer finds that the clock in the motion relative to him tick more slowly than the clocks at rest relative to him. Okay. Thank you. Now the relativity of the time, the time dilation. We will discuss now time dilation with the help of Lorentz transformation equations. Let some event takes place in the moving frame. So this is our moving frame. This is rest frame. Rest frame S, moving frame S dash. moving frame S dash, moving frame is S dash, which is moving with velocity u, moving frame is S dash, which is moving with velocity v along the x direction. So some events takes place in the moving frame and recorded time in the moving frame is, t2 dash minus t1 dash is the proper time, t0. Because we are in the moving frame and we notice the event, and that time will be the proper time. So this is the proper time. Okay. Now the same event observed by the observer, which is at rest, which is in the rest frame, recorded time is now t. So this t will be different. This will be the non-proper time, because according to this observer, the observer as the frame S dash is moving, so that's why, and event took place in the moving frame. So according to Lorentz transformation equations, the relation between non-proper time and proper time is, please go through my video that is on the Lorentz transformation equation. You'll find this relation there. So I will give you the link in the description of my video about the Lorentz transformation equation. This equation you will find there in my video regarding the Lorentz transformation derivation. Okay, so this is non-proper time, and this is the proper time, because it is noted by an observer where the events is happening. So we write down, because the event started at time t1 dash and ending of the event is t2 dash, the same time measured by the observer, which is at rest, okay, in a different place. So that will be time t1 and t2. So the non-proper time is t2 minus t1, substituting here, substituting the values. So we are having the relation between non-proper and proper time. Okay, so this is proper time. So proper time, this tau is greater than tau naught. Since the event takes place in the frame S dash and recorded there, when it is recorded there in the moving frame, that time is the proper time. But when it is recorded by the observer, which is at some different place, that will be the non-proper time, that is tau, that is t or tau. Okay, and tau is, or t is greater than t naught. So in motion, the event times delayed. So this is called time dilation. Okay, thank you. Please subscribe my channel.